All right, so we're going to start. It is my great pleasure to introduce our speaker today, Steve Miller. He is a professor at Williams College and also has a joint appointment at Carnegie Mellon. Steve, he was my first co-author of a paper. Steve has graduated from Yale with a Bachelor of Science, and then he did his PhD at Princeton. And since then, he's been some sort of an earthquake in number theory and all sorts of areas. It's not strange for Steve to go to departments and then all of a sudden you realize that he knows people in the probability. In probability, he knows undergrads, he knows grads. He knows people in number theory, analytic, algebraic number theory. He is one of these people that I don't know where he finds his time. If I write an email, regardless of time, there's an answer within seconds. There's only two people I know. One you know, which is Keith Conrad, and Steve Miller. They both have this quality of being responsive 24/7.
And God help you if you email us together.
Yes. You haven't written a paper with Keith.
No, but we will.
Oh God. Okay. So, well, in any case, Steve has found time to write 5 books published, one on its way. Steve has co-authored some 131 papers, and there are another 15 under review at least. And he is the faculty president of Williams Phi Beta Kappa chapter. He has a long tradition of empowering anywhere from undergrads to grad students. Myself, when I met him, he has co-authored many of his papers with students. He directs the small program at one of the most the well-known RUs in the country, which every year, I don't know how else, they produce papers after papers of like in a few weeks the great research that they do. Steve has joined the 2019 class of Fellows of the AMS, and the note there is for contributions to number theory and service to the mathematical community, particularly in support of mentoring undergraduate research. That says it all. Steve?
So, thank you.
Thank you.
So it is always a pleasure to come back here where I, as has been said, intersect with a non-trivial percentage of the people in the room. One correction, though, I'm actually not giving the talk by myself. The audience is going to be participating, and this is your chance to show your parents and other honored guests just what you've been doing for the last couple of years. So what I want to do today is I want to show how the math you've been doing can be used to solve real problems, and how problems in the real world can inspire good theory. So a lot of times my students say, I don't know enough to be valuable. Yes, you do. You don't have to get to the best result. You just have to do better than is being done. And that's a bar I can often exceed. All right, so what I want to talk about today is the German tank problem. Out of curiosity, how many people are familiar with this? Okay, your voices are going to be sore, and I don't think you'll be able to say too much today. Sorry about that. All right, but for the rest of you, I would like to hear some suggestions and thoughts as to what we should try to do. All right, so just a brief introduction. There's a nice video if you want to click on it over here. Here's 2 snapshots of Europe at the start and shortly into World War II. And you can just see the expansion of the Third Reich. And one of the reasons they were so successful was very good strategy in terms of how to use tanks. It became very important for the Allies to find ways to blunt the attack. One of the things they needed to know was how many tanks did the Germans have? How many were they producing? How many were in the field? So, how can you find the number of tanks? Thoughts? Any ideas as to how you might try to find how many tanks the Germans have? Yes?
You can count them.
Okay, but how would you count them? So, you can count them on the field of battle. So that is absolutely one way. What else could you try to do?
Production, maybe.
Yeah, you could try to put spies in.
No, steel production, steel.
Oh, look at how much other things are being used. Absolutely.
Sampling.
sampling. And so given that this is a math talk, it is almost surely the sampling that is going to be coming to discussion. Now, sometimes you're actually lucky, and the other side writes books about what they're doing. So if you've ever seen the movie Patton, there's the brilliant scene where he goes, "Rommel, you magnificent bastard, I read your book," where he actually knew what a lot of Rommel's tactics were because Rommel wrote a book about the infantry tactics in World War I. Usually you're not going to be that fortunate, and we actually do have a job, which I guess is good for us. Right. So here's the original formulation. So you observe some number of tanks in the field, and let's say you observe the serial numbers, S1, S2, S3, Sn. Maybe these are from destroyed or damaged tanks, and you want to try to estimate how many tanks are in the field or how many tanks are being produced. Right. So initially we assumed that the tanks started with the number 1 and they go all the way up to n, and you want to try to estimate what is your best guess for how many tanks will produce or in theater. The more general problem is maybe it doesn't start with number 1. And if anybody can point to this in the literature, I would love to know this because I'm in the process of writing this up right now. I haven't been able to find in the literature starting with a variable starting tank. You can actually do with very similar mathematics, which is really nice. There are a lot of reasons why you might want to have tank numbers consecutive. It makes it a lot easier from a maintenance perspective, where you can quickly look at the serial number and get some information. But it can also be bad because your enemies, as we will see, can use this to glean information. If you ever walk into an exercise room, you might hear someone go, 98, 99, but they might really be at 2 or 3. So they might be starting off with a different number to try to mislead you as to where they really are. Right. So there are severe dangers in over or underestimating how many tanks the enemy has. So anybody want to give me either a danger of over or a danger of underestimating?
Underestimating seems pretty obvious.
Okay, so what would be? I have learned that what seems pretty obvious is not always pretty obvious, so sometimes we have different definitions. So what would be a bad consequence of underestimating?
You're going to send in too few tanks.
You will send in too few tanks and you will be routed.
Right.
Overestimating. Yes?
You wind up building too many and wasting resources.
You waste resources and you waste time. So one of my favorite quotes, there's many different variations of this. Lincoln to General McClellan, or I'm sorry, to one of his aides. If General McClellan isn't going to use his army, I'd like to borrow it for a time. And so if you look at the Battle of Antietam and some of the other battles, McClellan was extremely cautious. And he did not take the advantage of how the Army of the Potomac was relative to the Army of Northern Virginia. And he could have really pressed the attack more in several situations. And so he always felt that he was outnumbered. Right. So for the talk, I want to talk a little bit about the mathematical preliminaries. I want to make sure we're all on the same page. So I will quickly go over some basics from combinatorics. And this is really all we need. I'll talk about how to solve the original version of the German tank problem and just sketch the details of how you would do the more general case. I know everybody wants to see all the technical algebra details. That's why they're in an appendix that you can look at later. And then if there's time, I will use this to talk a little bit about how you can use statistics, how you can do regression, and how you can actually get conjectures. So one of the things that I really want to emphasize is how do you get a rough sense of what the answer should be? What kind of data can you collect? How can that influence things? Before you start gathering data, can you get any rough idea of how you think things will behave? All right, so preliminaries. So hopefully this is pretty much review. N factorial is the number of ways to order things where things matter. So think president is different than vice president is different than secretary. N choose k is the number of ways to order things when order doesn't matter. Think House of Representatives. And then the last is the binomial theorem, x plus y to the n is the sum of n choose k, x to the k, y to the n minus k. And if you think about this, when you expand this out, you're going to have some number of x's and some number of y's. If I choose kx's, I choose n minus ky's. How many ways can I choose k of the factors to be x? That's n choose k. All right, a couple of results on Pascal's triangle. First is the formula n plus 1 choose k is n choose k plus n choose k minus 1. There's a lot of ways to prove this. One way is unenlightening algebra. Just put in what they are, cross multiply, have the dust settle, and you're there. A better way is to tell the proof through story. And so let's assume that there are n Red Sox fans and 1 Yankee fan. And we want to form a group of k people. How many ways can we do this? So a lot of combinatorics comes down to telling a story. And you relate what you want to compute to something that you can do that's equivalent. So if I have n plus 1 people and I want to choose k, the number of ways of doing that is just n plus 1 choose k. Now let me condition on whether or not I choose the Yankee fan. There's 1 choose 0 ways not to choose the Yankee fan, and then I have to choose K Sox fan. Or if I'm unfortunate, if I have the Yankee fan, 1 choose 1, then I have to choose K minus 1 Red Sox fans to balance them out. And so there is a proof by story. All right. The next identity we need for Pascal's triangle is some of the interesting properties of it. We don't really need this one, but since it's a talk, it's nice to show some fun things. So this is actually related to the previous picture. How many of you have seen this connection out of curiosity? A few people. I know there's some people who do fractals or talk to people here who do fractals. So if you take Pascal's triangle, and every time you have an odd number, you put a dot, and every time you have an even number, you just delete it. You can ask what kind of shape do you get as you let the thing grow further and further and further. And you'll actually get Sierpinski's triangle. What I've done is to make this, I actually rotated it 90 degrees. It was just a little bit easier like this. I've got a little animation over here where if you want, you can just click on it and it will show you adding more and more rows, constantly rescaling the window so that you always have it from 0 to 1. So we don't really need it today, but it's hard to talk about Pascal's triangle without showing some of the fun properties. The one we will need is this result. The sum of m goes from k to n of m choose k is n plus 1 choose k plus 1. And this is actually the key to the fact that we can get nice closed form expressions for what happens. It's very easy in general mathematics to write down equations. The question is, will the equations be tractable? Can you extract something from it and actually get a sense of what it's saying? And this over here, this identity, is the reason we're able to do so. It's the reason the algebra will work out later. You can do a combinatorial story for this related to either the stars and bars problem or the cookie problem. If you're familiar, I'll do the more brute force. If you just look at what this is saying is if I sum along m choose k, so here's k equals 0, here's k equals 1, it then relates this value to one more at the next level. So 1 plus 2 plus 3 plus 4 plus 5 should be 15, 15 here. 1 plus 3 plus 6 plus 10 is 20, that's the one over there. Proof by picture. Okay, no, can't prove by picture. But the proof by induction isn't too bad. So you check the base case is trivial, and then you just say, well, okay, I've got my sum, and by induction I know what my sum is, I add the next term, and then I just use Pascal's identity, and it follows immediately. So it's a nice property. All right. So the original version of the German tank problem. So this is the part where I'm going to want you to start making some conjectures. So how should n hat, our best guess for the number of tanks in the field, depend on m, which will be the maximum serial number we observe, and k, the number of tanks we observe. So we will assume that the first tank is 1, the second tank is 2, etc., etc., etc. Nowadays, in the real world, you often encrypt the serial numbers so that they are no longer consecutive integers, and there's a lot of companies that do stuff like this. So does anybody want to give me any information about how I should estimate n hat as a function of m and k? What's the first thing I should know?
Hat should be bigger than m.
Yeah, it should at least be m. Right? If the tank numbers are consecutive and I observe something with serial number 100, if I have a guess that there's 90 tanks in the field, it's going to be hard to justify my salary. So it's going to be at least m. How much more than m do you think it should be? So it's going to be m plus something, I agree. So let's write it as m plus g of mk. The simplest possible guess is maybe it depends linearly on m and with the reciprocal of k. The more tanks I observe, the less I think I need to inflate my value. And the higher the serial number I observe, maybe the bigger I expect it to be. And then it's not clear what that constant b should be. But this is a very reasonable guess to make. It turns out it's very close to the actual answer. The actual answer is m 1 plus 1 over k. So there's m, and it would be like b equals 1. And then we have this extra minus 1. Whenever you get an equation, if you can, you always want to do a test. Is this reasonable? Is this plausible? Can you think of any tests that we could do to see if this is a good formula?
You calculate like the expected value that you're going to find so many numbers.
Okay, that's a lot of work to calculate the expected value. I want it easy. I don't want to do much work. I mean, you told me I didn't have to do much work when I came here.
If you put M equal N, right?
Ah, good. So imagine we actually observe every tank. So if K equals N, so if we observe the number of tanks equal to the number of tanks, then we should get back N. And so if we take K equals N, then M would have to equal N as well. And N over N will be 1, which will cancel the minus 1. So in the extreme case, when every tank is observed, you can see the illumination. It works. There's another extreme case you could do. You could take K equals 1. You observe only one tank. If you observe just one tank, where do you think that serial number will be? Probably in the middle. And so you would essentially want to double it, and that's what's going on here. So it is a very reasonable formula by looking at some of these extreme cases. All right, so now let's start getting into the nuts and the bolts. Oh, well, not the nuts and bolts. We're not actually going to work with physical tanks. So let's let M be the random variable for the maximum number we observe. And we want to calculate what is the probability M takes on different values. Well, it clearly can't be less than K, because we observe K tanks. And it can't be greater than N, because there's not more than N tanks. So in those ranges, the probability will be 0. And then if we are between K and N, the probability is either one of these expressions. And you can prove it with two different stories. So this is the number of ways I can choose a sample of K tanks from N. Now I have N tanks, I choose K of them. How many of them will have the largest tank of M? Well, if the largest tank is M, then that means I have to choose K minus 1 tanks from 1 all the way up to M minus 1. So that's this expression over here. Another way of looking at it is, this is the number of ways I can choose K tanks where the largest value is at most M, but it doesn't have to be M. This is the number of ways I can choose K tanks where the largest value is M minus 1, at most M minus 1, but it doesn't have to be M minus 1. So the difference would be the number of ways where it's exactly equal to M for the largest value. And then you can just do a little bit of algebra to show that the two are the same. All right, so now as was commented, now we'll do the expected values. So the expected value of a random variable M is you just take each possible value and you weight it by the probability that it equals that. Is it possible to switch clickers? Or no?
You sure you have another one?
I have another one. There is a reason to switch clickers. Extra credit if anybody can tell me why.
It's a different color.
It's a different color. The green color actually records better on the computer than the red. And I will trust Alvaro not to take the other clicker and play with it. I did that to somebody once during the talk and said, yo, it's all controlled by hand motions. Okay, good. All right, so the expected value of M is just going to be M times the probability that M equals little m. And so we just plug in what's the probability, and we'll get M times that. So the question is there a nice closed form expression from this that we can do stuff with? All right, so it's time to do a little bit of algebra. We put in our answer, we expand out what the binomial coefficients are, we do some cancellation, and we just group things well. And we can say this is beginning to look like an M choose K maybe, you just multiply things around a little bit, and we get a sum of M choose K over here. And we have a closed form expression for that sum in terms of another binomial coefficient. And that's why everything works out, because this sum has such a good expression. Now that we have this, we can now expand for what n plus 1 choose k plus 1 is. And now we can do a lot of cancellation. You see an n plus 1 factorial over an n factorial. When the dust settles, you get a really nice k n plus 1 divided by k plus 1. And so just rewriting this, we now want to just solve for n, and we get n is the expected value m, 1 plus 1 over k minus 1. And so if we now want to estimate the number of tanks, all we have to do is we replace the expected value of m with our observed value. And if you love stats, you can prove lots of things about what kind of estimator is this. It's a really good one. It has a lot of nice properties. It's also very simple and very easy to work with. So any questions on this part over here? So as long as, yes?
Is this something that they use?
So this was actually done in World War II. So there were two different approaches to try to estimate how many tanks the Germans were producing. One was through spies, and one was through a statistical analysis like this. Which do you think did a better job? Yeah, I wouldn't be giving this talk if the spies did a better job. Right? So this is a conditional probability question. Right, yes?
Where is the serial number of a tank?
On the turret.
Where in the tank?
I do not know where it would be. But there would definitely be a place where some of the stuff. And
Isn't it the big numbers on the side of the thing? Is that not the serial number?
No, the driver should know which one to get into.
Yeah.
But you can have serial numbers on lots of different parts. So you could look at maybe the serial number on the engine or the serial number on this or that. And so there's a lot of different things you could use almost as a proxy for when was the tank made or which tank is which. Okay. So let's talk a little bit about the new formulation. So what we're going to do now is we don't know what the smallest value is. So it's going to be an extremely similar analysis. So we're going to talk about the spread now. So n is going to be the largest minus the smallest plus 1. Okay? And then s is going to be just the largest value we observe minus the smallest value we observe. So if you wanted to guess something for how many tanks there are, very similar to what we did before, what would you say your first part of your formula has to be? Your best guess for the number of tanks is? What does it have to start with? Yes?
The number observed.
Which number observed?
Number of tanks.
We don't observe any number of tanks. We observe a bunch of serial numbers.
Oh.
And we have M1 is the smallest serial number observed, M2 is the largest serial number. So as a function of S, what would the start of our guess be for the number of tanks? Yeah, it has to start off as S, right? We've observed a spread like this. Well, let's think for a second. If you observe tanks at 1 and 2, what's your spread? 1, but there's actually 2 tanks. All right, so there might be a +1 or -1 floating around for a problem like this. When you have a large number of tanks in the field, that +1, -1 is not going to make a big difference.
Right.
If I can get what's going on to within 1, I'm happy. But this is one of the problems of how you count integers. Okay, so it's got to start off with an S. And then you might guess it's going to be corrected in a very similar way. So I'll guess that maybe it's S plus G of S over K. And I'll guess G is of the formula B, S again, very similar to the MS, divided by K minus 1. So why do you think it's divided by K minus 1 now and not K, which is what we had last time? So we're the stats people. How many people have taken a stats class? Not that many hands. Okay. So one of the things you see in a stats class is how you calculate standard deviations of samples. You always have to be careful of the number of observations you have. Imagine I want to try to estimate some population parameters. Does everybody know what the mean and the standard deviation are? Okay. If I give you a sample with one data point, what is your best guess for the population mean? That point, okay. Not a big deal. What's your best guess for the variation when you only have a sample with one data point?
0.
Ooh. I want to say you're not allowed to guess. Maybe 0 is a fine guess. But if you only have one data point, you can't talk about the observed variation because there is none. So your formulas should break down if you try to use them with only one observation. So it's actually a good sign to have something like this. So it should really be depending on K minus 1 and not on K. I need to have at least 2 points if I want to see a spread. And the actual answer is pretty similar as 1 plus 2 over K minus 1 minus 1. And again, you can check the extreme cases. What if K equals 2? What if K equals n? So we've observed all the tanks. Does the factor of 2 here seem reasonable? We had a factor of 1 the last time. Is that surprising or does that seem good? Well, the last time we knew we started at 1 and we were only going in one direction. Now we actually have 2 directions that we're going in. So a factor of 2 seems reasonable. So whenever possible, I always want to try to ask, is this formula reasonable? Alright, so you can calculate exactly as before, what is the probability that the spread equals S? And you're going to have extreme cases. You've got to have at least k tanks. So what's the smallest possible spread? It's going to be k minus 1. So the probability will be 0 if it's too small, it'll be 0 if it's too large, and you can play the same games as before. And so this is just summing over where certain things are. It's very similar to the calculation we did. And then the rest of the proof is similar. We use the same identities, and we again luck out and we have closed form expressions. And it's very weird to get closed form expressions. So I like to tell my students the great lie of calculus 2, and I know we just had awards for calculus, is that you can integrate. You can't integrate. Neither can I. Nobody can integrate. In general, if I give you a function, it is unlikely to have a closed form expression for the antiderivative. But because we care so much about our students, we professors spend so much time looking for functions that have nice antiderivatives so you could actually write something down. Until we get to multivariable calculus, then we just throw up our hands in frustration because you can't really integrate over the general regions and get this nice result. But whenever you have a nice result, even if it's not a perfect description of the world, it might be a good enough description to do something meaningful. And so it turns out the rest of the algebra is extremely similar. It's in the appendix. There might be enough time, but I don't think there's enough desire to go through it, so I'm not going to bother going through it. This is one of the best tables I've ever seen. It has to be right because I found it on Wikipedia. And this is an analysis of how well the statisticians did versus how well the spies did. And so you can argue, well, this was 271, this is 241, 10% of the off by. All right, an error like that is very small compared to errors like this. And then there's a lot of things you could ask about why the errors were this large. If there are some common features going on, you can maybe try to adjust the data to take stuff like this into account. One of my favorite stories goes back to astronomy. So classically, how many planets did people know about? I'm sorry? That's not classically. Go back to the Greeks. How many planets did the Greeks know about? Which ones?
The inner planets.
The inner planets, Mercury, Venus, Earth, Mars. What else? Jupiter and Saturn. And for a long time, that was it. And then in the 1700s, Herschel discovered another planet. Anybody know the original name he proposed? I will not risk Latin. My Latin is not good, and it's not actually meant to be spoken, so I think I'm excused. But the English translation is basically King George's star. King George was his sovereign, and in one of the greatest ass-kissing moments in all of history, decided to name the planet after his liege, who thought this was a wonderful idea. The rest of Europe said, hell no. And after negotiations, they decided to name it Uranus. Jupiter, Saturn, Uranus, if you look at the progression of the Roman gods in terms of who was the father of whom, worked very well. And so we then had a couple of decades where we had one more planet and then that was it. And then eventually it was discovered that the orbit of Uranus was not quite matching the prediction from Newton's law of gravity. And so one possible explanation is Newton's law of gravity is wrong. But it's done so well in so many situations, it would be a shame to throw away Newton's law of gravity. So you could propose maybe there's another planet further from the sun, so it's really only affecting Uranus that much and the other planets not so much. And so there was a search to find this planet. And there were two different teams, and unfortunately for one person, he couldn't convince the people at the observatory to point the telescope where he said the planet should be. And this was Adams, I believe, in Britain. And so I think it was Leverrier in France who was the first one to actually discover it. And this was basically like a rock star moment of the 1800s to predict with paper and pen, paper and pencil probably, where a planet would be. And once he had this, he had an incredible reputation. And then they turned and they looked at other parts of the solar system, and the orbit of Mercury was just a little bit off. And so a lot of this is coming from a great article by Isaac Asimov, where he talks about this whole story. I think it's called The Planet That Wasn't. And so the orbit of Mercury is a little bit off. You've just discovered Uranus to fix the orbit of Neptune. What are you going to do to fix the orbit of Mercury?
Suppose there's another planet.
Yeah, suppose there's another planet. It's going to be somewhere between the Earth, somewhere between the Sun and Mercury. Anybody know what the planet was called?
Hell.
I give people 2 hints. Vulcan. After the Roman god of the forge. The planet's very close to the Sun. Vulcan is probably a pretty good name for it. And so he predicted where it should be. The only problem is, given how close it is to the Sun, it's going to be very hard to observe. So when you're looking at it, you're going to be staring directly into the Sun. Well, but when there's an eclipse going on, that might give you a chance to see it. So when the first eclipse came where there was a chance to see it, people pointed their telescopes at it. What do you think people saw? Most people saw nothing. And some people insisted that they saw the planet. And this is the danger when you think you know what the answer is. When you have a bias. This is why I'm taking such a long digression. I really want to drive home this because it's so tempting when you know what the answer is, or when you think you know what the answer is, to adjust your data to match your preconceptions. I want to be known as the person who was the first one to see Vulcan. Yeah, that was it right there. But they weren't good confirmed recordings. And so as time passed and people got better and better telescopes, they were able to say, well, if Vulcan exists, its mass can be at most, it keeps shrinking. Until eventually, we were pretty sure that at most you have is a few asteroids, and that's not going to be enough. And the eventual solution didn't come until Einstein, with E equals mc squared, and basically attributing some kind of mass to the gravitational force, which then fixes Mercury and propagates outward. And Isaac Asimov has a beautiful pun about all of this. It's worth reading the article. I'm pretty sure it's The Planet That Wasn't. And the reason is, maybe there is some biases in how the spies are working. And once you have a number, maybe that's going to affect your numbers for the future months. And then once you get into a local long answer, you're going to stay there. So it's very easy to get caught in something like this. So to me, this is an absolutely wonderful picture in terms of just how well you can do by using mathematics. Now, if you're the allies, who do you believe? Do you believe the spies? Do you believe the statisticians? Mathematicians? Or what could you do?
Split the difference.
Well, so one thing is you could split the difference. How would you split the difference? You could do the geometric mean, you could do the arithmetic mean, you have lots of different ways. And so you could try to decide maybe how much weight to give to each one of them. But if one of the observations is not valid, you don't want to give weight to it, but you don't necessarily know which one is valid or not. And so a huge part of any career in math and stats is being able to convince the people who can say yes, that they should listen to you. Okay, so for the last couple of minutes, I want to just talk a little bit about regression. Given that there was not an overwhelming number of hands that were going up when I talked about statistics, I think that this is a good thing to see, especially if we have some seniors who are about to go off into the real world. All right, so there's a very common problem of trying to find the best fit line or the best fit curve to some data. And you might have some proposed relationship. And we have lots of different ways of measuring errors. So I believe that there's some linear relationship so that y is axi plus b. And I can measure error by looking at either the difference, the absolute value of the difference, or the square of the difference. So I have 3 candidates. Is there anybody who can say something good about this error? Yes. It's easy to compute. This is 21st century America. Easy to compute is worth a lot. Unfortunately, it has some severe disadvantages. What is a disadvantage?
How about giant amount of cancellation?
Yeah, you could have a giant cancellation. Imagine I want to find the best fit line. Let's pretend that this is a perfect square going through this point here and this point down here. Does everybody agree that this would be the best fit line? Well, you could actually draw the line going in the opposite direction. And because the errors are signed, the error here would cancel out and you'd have a perfect fit. So the problem is that negative error could cancel a positive error. So the first one, in the words of Monty Python, is right out. 2 and 3 are now at least natural candidates. They only have non-negative errors. What's an advantage of 2? What's an advantage of 3?
3 is computationally easier.
3 is computationally easier. We can square is nice. Calculus is available. Right? We've got several prize-winning calculus students here. Absolute value is not differentiable. So we can use calculus if we do the third choice. The way I like to phrase it is if I'm hired as the consultant, I like to use 3. And if I'm doing the hiring, I like to use 2. Because here with 3, a large error is magnified tremendously by squaring. So 1 error of 2 is much worse than 2 errors of 1. And this can give too much weight to a bad observation. All right, so let me just show you a little bit about how regression like this works. Basically, multivariable calculus is a single variable calculus just done multiple times. If I want to find the best fit values to minimize the error, I just take the derivatives with respect to a and b and set them equal to 0. When you do a little bit of algebra, you get a nice matrix equation, and you can explicitly solve for a and b. And that's wonderful. You don't have to do any numerical simulations. You get an explicit formula. Now, if I have a matrix like this, what do I need to know about this matrix? So what should be true about this matrix? If I want to be able to solve the equation.
Non-singular.
Non-singular. The matrix has to be invertible. There is only one way that this matrix is non-invertible. And that's if every xi is the same. So think about it. You want to see how y depends on x, and you always observe at the same value of x. There is no way in hell you can get y dependence in a situation like that. It should break down in flames, and it does. As long as there's some variation in x, you will be able to solve it, and you will get answers for a and b. So let me talk about why this is so useful. It works even if the relationship is not linear with a change of variables. So why do we like logarithms so much? Because logarithms can linearize a lot of products. So imagine we have y equals bx to the a. Well, then if we take log of both sides, the log of y is a log of x plus b. And so now we have a linear relationship. And so, as you can tell, I love astrophysics. Kepler has 3 laws. The first is planets move in ellipses. The second is if you draw a line from the planet to the sun, it sweeps out equal areas in equal time. And the third is the square of the period is proportional to the cube of the semi-major axis u. This is one of these is not like the other. This is a far more complicated law. And so let's imagine we believe that the period squared is proportional to the length cubed. Well, imagine we don't know this. How could we sniff out a relationship like this? So how did Kepler get something like this from data? Well, I can, of course, take the square root of both sides and get some new constant. Whenever you see something introduced as a b tilde, that's a pretty good indicator that's going to be changing on the next line. So t is b L to the 1.5. I can just renormalize like this. And so more generally, if I take logarithms, things will be nice. So here is the semi-major axis of the planets. Here is the orbital periods in years. And based on these units, anybody want to guess what b should be? If you look at the data carefully, you should be able to figure out what b is. Well, at least approximately. Any of these numbers down here particularly nice? Yeah, basically the Earth, and that corresponds up here to a 1.000. So b should be 1 in this units, or close to 1 in this units. We're basically choosing units of measurement that are nice. So there's a lot of fun units of measurement. Out of curiosity, has anybody heard of the Bruno, the Millie Helen, the slug or the smoot? Smoot, yes. Millie Helen? Bruno. So afterwards, I'll talk about some fun units. But this is a good scale to use because it's going to make our constant be nice. Okay, and so this is just highlighting the two ones. Okay, so here is a plot of the log versus the log, so log-log plot, and here's the best fit line. And it does a phenomenal job. I have sadly followed modern convention and I'm only including 8 planets. Times have changed since I was a child. I actually know a person who knows the person who had to hit enter and officially downgrade Pluto status on the international data set. And they told me they didn't want to do it, but they had to. Phenomenal that you can sniff out the relationship. We don't need to know that the exponent is 1.5. When we do this, we see a beautiful linear relationship with slope 1.5. This is the power of being able to do very simple data analysis. This is just for the people who know what smoots are. All right, so I will quickly do the birthday problem. How many of you have heard of the birthday problem? Okay, almost surely there's enough people in this room, so I'd be fine. How many people do you need to have in a room before you have at least 2 people with the same birthday? And you'll assume, for instance, no one is allowed to be born on February 29th, all days equally likely, no identical twins, please. You know, make it a fair game.
About 24.
It's around 22.
23 or 24, I forgot.
Something like that. And so a straightforward analysis shows that it's about d to the 1/2 log, square root of log 4. And when you look at data, you can actually get the exponent of d equals 1/2 without too much trouble.
You might be amused to know that 3 of my 4 children have the same birthday in different years.
Wow.
I will ask a follow-up
That's
question,
about
and this
one-
is not being recorded.
It's about 1/3,000.
No, that is, how close was the 4th?
Not close.
Not close, okay. And I also have to ask the following, are any of your children adopted?
No.
Okay. Because if they're adopted, then this is not as impressive. So here's trying to look at the best fit line for like the German tape problem. I'm looking at n minus m. And trying to find the best fit line, because I know I've got to have at least m for my guess. It turns out you are not allowed to do this. And the reason is I'm putting the m that I'm trying to observe on both sides of the equation. And if you look at it, it kind of breaks down and says you should not be doing this. And so, I won't go into too much detail. This should either look like a really good plane, or for those of us who are still celebrating Passover, a piece of matzah. And you can see the linear plane, as opposed to, I guess, the non-linear planes. The plane that's coming when you try to do the best fit plane to the German tank problem. That you can really get a sense from the data as to what the value should be. Well, it seems like on the screen, the last line is being cut off, but it would have been beautiful and would have shown you just how great these exponents are to what they should be. All right, so just briefly end. We have 2 or 3 minutes? All right, so since we have 2 or 3 minutes, this is the reason why you should always use this class file, because you can go backwards very easily. All right, so this is the Harvard Bridge. It's about 620.1 meters. Anybody know how many smoots it is?
1.
So smoot was a pledge, I think back in the 1950s, 1960s.
Plus 1 here.
Plus 1 year, plus or minus 1 year actually. So smoot was a pledge at a fraternity at MIT. And what the fraternity wanted to do was know, I wonder how many of our pledge it would take to just measure the whole bridge and say, hey, smoot. And so they would pick him up, mark, pick him up, mark, pick him up, mark. So it's like 367 plus or minus 0.1 plus or minus in the year. Well, Cambridge didn't find this amusing, and so they had the bridge repainted. This didn't deter the fraternity, so they did this again. And it went back and forth, and finally Cambridge said to hell with it. And now they actually have beautiful smooth markings on the bridge that tell you exactly how many smooths you are from an end. And if there is an accident, they will report where the accident was in smooths from the end of the bridge. It's become institutionalized. And so in terms of just where things end, seize opportunities. You never know where they will lead. So this is Smoot. Obviously not from his college days. Anybody know what Smoot did with his life? You can't, yes?
He's the president or chairman of some medicine standard organization.
Yes, you can't make this up. The American National Standards Institute, president of the International Organization for Standardization. Well, for those of you who are padding your CVs, or for those of you who don't need to pad your CVs, you have a unit of measurement. It looks really good for stuff like this. So, thank you.
Very nice. You have any other questions? Like, what's up, Bruno?
So Bruno is the volume in cubic centimeters from dropping a piano, I think it has to be a grand piano, off a certain 3-story building at MIT. They were not responsible for the Millie Helen.
Any other questions? Okay, let's thank Steve again.
They know how to turn it off?
I don't know anything.
We'll turn it off. Okay.
Thank you very much, and thank all of you for coming and hopefully enjoying the presentation. It's beautiful and very amusing sometimes presentation, I have to say. You're living up to the reputation of the Williams College speakers who come here.
Thank you.
They're always interesting.
Yeah, every time. Boy, it must be fun to be in that crowd.
Challenging, but inspiring.
Yeah, and again, congratulations to all those who received some recognition today.